Welcome back, everyone. Today we'll be looking at AS and A-level chemistry, ionization energy, and electronic configuration. So let's look at the definition. The first ionization energy is the energy needed to remove 1 mole of electrons from 1 mole of atoms or molecules in the gaseous state to form 1 mole of 1 plus ions. Do not forget to state it's in the gaseous state, and the equation is denoted by this, where Mg, for example, we're taking magnesium here, which is in gaseous state, which forms a 1 plus ion, and electrons are shown. Do not forget the gaseous state and the electrons. Okay, so ionization energy is endothermic. Why? Because the bonds between the nucleus and the electron is broken. As we know, energy is supplied to break bonds, and energy is released when bonds are made. All right, that's an easy way to remember it, and it'll be easy for you to understand what you're doing, and it'll be much easier for you to answer if you know what you're doing. So this is a good and intuitive way to remember why ionization energy is endothermic. Okay, subsequent ionization energy increases as we take out electrons as the effective nuclear charge increases. This is a keyword and it might have changed, so please check your syllabus. But usually marks are just given for effective nuclear charge increases, and there's a larger attraction per electron. So there's a net larger attraction per electron, and more energy has to be put in to liberate the electron. So this chart shows that subsequent ionization energy increases. For lithium, it increases from 519 to 7,300 and then to 11,800. There's an extremely large jump over here, which shows that lithium is a group 3, is a group 1 metal. This is because, I will get to this. I'll explain this in much more detail, but you can gauge which group the metal or element lies in just by the changes in ionization energy. For example, in this case, there's a large increase from the first electron removed to the second electron removed, which shows that it's a group 1 element. So basically, if there's an extremely large change in ionization energy, it's due to the fact that the next electron is being removed from another or a lower electron shell. So this is from the valence shell. This is a second shell, and this one is there's another change in shell. So this would be 2 electrons here, which is the energy level equals to 1, or the shell closest to the nucleus. Take note of the y-axis, which is in log to the base 10, and please use the correct data points when comparing data in your examinations. To summarize, if there's a large change in ionization energy, it means that the next electron shell is the next electron is from a lower electron shell. So we know that lithium is a group 1 because it has 3 electrons, and this is in the first there's an increase, so it shows that it's a group 1 metal in this case. So these two are from the inner shell. So 1, 2, as we all know, the first shell always has 2 electrons, and the second shell has 8 electrons. So this is from the second shell, and since it only has 1 electron in the valence shell, is in group 1. Okay. So previously we know that electrons orbit the nucleus and are found in shells around the nucleus that oscillate around the nucleus. The electrons oscillate around the nucleus in a shell. So previously, first shell contained 2 electrons, second shell contained 8 electrons, and the third shell contained 8 electrons as well. And the electronic configuration was of the form 2.x.y, where x and y are digits. For example, 2.8.8 or 2.8.8 or 2.8.1. So however, that has changed now. We use orbitals. Okay, an orbital is a region where an electron has the highest probability of being found. So, and their characteristics are they have a fixed shape, and each orbital contains 2 electrons. All right, you see these shapes here. These are the shapes for each orbital. S orbital has a spherical shape, P orbital has a dumbbell shape, and the D orbital has a four-leaf clover type shape. You don't really need to know the d orbital for AS, but it will be tested for transition metals in A levels. All right, so there are 3 orbitals: S orbital here, P orbital, but okay, P orbital has 6 electrons, right? But I just said there's 2 electrons. So where do the other 4 electrons come from? So if you look at this is in the z-axis. So one dumbbell is in the z-axis if you follow my mouse. Another dumbbell is in the y-axis. and another dumbbell is in the x-axis. So overall, there are 3 dumbbells or 3 orbitals, and each orbital contains 2 electrons. So the the p shell or p orbital in all contains 6 electrons. The d orbital contains 10 electrons, and there are 5 orbitals. You don't really need to know the arrangement, but they're between the axes, and then they also have their different shapes that I'm not going to get into right now because you don't need to know it for AS. But just know that they have 2 electrons in their fixed shapes. You may be asked to draw these ones out in your examination, so please remember the shapes. Alright, energy levels and their orbitals. Energy levels are similar to the number of electron shells that we've learned in IGCSE or O levels. So n equals to 1, it has 1 s orbital because it contains 2 electrons, right? So as we already discussed, one orbital contains 2 electrons. So n equals to 1, the smallest, the closest shell contains 2 electrons, and it will only have one orbital, which is 1s. 1 denotes the energy level, and S denotes the orbital. We'll get into further detail in the next slide. So n equals to 2, we know that it has 8 electrons. Sorry, there's a typo over here. So 2s contains 2 electrons, and 2p, as we know, contains 6 electrons. Remember, this 2 does not refer to the number of electrons inside the subshell, but it refers to the energy level that the subshell is in. N equals to 3. Previously, we used to know that it contains only 8 electrons. However, there are transition metals now. You have to consider transition metals now, and they contain there's an increase in 10 electrons in the third shell, that's why it has 3s, 3p, and 3d, 2 in 3s, 6 in 3p, and 10 in 3d, which gives us a total of 18 electrons. So electronic configuration, the order of filling up is 1s, 2s, 2p, 3s, 3p, 4s, and 3d. This chart or this illustration over here depicts the energy level, and we must and just take note of this: electrons are always removed from the higher energy level first. Despite the fact that 4s is filled before 3d, when it forms ions, electrons are always removed from the 4s subshell. So if you look at this chart here, so 1s, this will be filled first, followed by 2s, 2p, 3s, 3p. 4s fills first, and then 3d, but 4s is technically on a higher level, so electrons are removed from 4s first. Okay, so conventions have changed as well. Like I said, 1 denotes the energy level that is from. S in this case denotes this orbital, and 2 denotes the number of electrons inside the orbital. So for neon, we know it's 2.8. So it's 1s2, which is in the lower subshell, lower electron shell. 2s2, because 2 and 2p 6. So 2 plus 6 overall give us 8 electrons. So 2.8 is represented in this case now. So just take note of this. And for sodium, which is 1s2, 2s2, 2p6, and 3s1, and since it has the same orbitals as neon, except 3s1 is in excess, we can change it to neon in square brackets. This is known as noble gas convention. You can use this as well. However, if they ask you in exams, just take note of what they're asking. Whether they're asking the entire electron configuration in terms of orbitals, or they're asking in terms of noble gas configuration. There are a few exceptions, which is chromium and copper. In the case where instead of filling 4s2 completely, they fill 3d5 and they 3d10. So just take note of this. The 4s2 is not fully filled. Alright, so just take note of these exceptions. So now we look into how to fill the orbitals based on a periodic table. So there's 1 electron in here, hydrogen, because there's 1 proton and all atoms or elements are uncharged. So number of protons equals number of electrons. So 1s1, 1s2, 2s1, 2s2. We'll look at this trend later, but the colors in red here, this one except helium, are considered the s block because they always start off, or they always end off with s orbitals. And the blue one is known as a d block because the final orbital that is filled is a 3d or d orbital, or 4d, sorry. In this case, the yellow one is called a p orbital because their final orbital that is filled is the p orbital. We look at that. or 1s2, like I'll begin from the start again. 1s2, 2s2, uh, sorry, 1s2, 1s1, sorry, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, 3s1, 3s2. So like I said, they will always end in s orbitals. And if you go back to aluminum, it will go back to 3p1. So it'll be 3s2, 3s1, 3s2, 3p1, 3p2. So they always end in p orbitals. And when you get to transition metals, so that will be AR plus 4s1, 4s2, 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, and so on. Just if you look at the like I said, 4s, the 4s orbital fills first, and you can also tell because of the s block placement over here. If you forget in your examination. Okay, that's how you fill the orbitals, and they will follow this order of filling up. Just remember that 4s, or the higher energy levels, when forming ions, the electrons are removed from the higher energy levels. And for transition elements, despite 3D being filled up later, electrons are always removed from the 4s. Also, do not forget the copper and chromium are exceptions when it comes to filling up the orbitals. So basically, each orbital will be filled up fully before moving on to the next one. However, in this case, neither 3D is filled up, neither 4s is fully filled up. And in this case, 3D is filled up while 4s is not filled up, despite 4s having a lower energy level and is usually filled up first. All right, let's look at drawing of orbitals. In this case, each orbital is depicted by a square, and 1s, 2s, 2p denote the orbital and the type of orbital that is there. So as we know, 2p contains 6 electrons and it has 3 orbitals, so there'll be 3 squares over here. And electrons always fill each empty orbital first and remain unpaired until there are enough electrons to pair them. So we can look at carbon, nitrogen, and oxygen. So if you look at the 2p subshell at the top, initially there's only 2 electrons in the 2p, so they do not pair up. They're unpaired in the individual orbitals. Increasing the number of protons by 1 and electrons by 1 to nitrogen. Again, nothing is paired. They always fill up empty orbitals first. And since in oxygen, and since there's no more space for since there's no more free orbitals to fill up, the electrons begin to pair up. It's more stable this way, and when it begins to pair up, there is spin pair repulsion, so which causes the electron to be repelled more and easily removed. I forgot to mention this, but remember to put your arrows in opposite direction, because electrons have a characteristic called spin, and the direction of the arrows represent the spin, and electrons with opposite spins are always paired up in this format. Okay, factors affecting ionization energy: size of nuclear charge, or the number of protons in the nucleus, which increases across a period. This refers to the number of protons in the nucleus. The larger the number of protons, the larger the attractive force between the electron and the nucleus. Thus more energy is required when the bond between nucleus and electron is broken. This stands true because the shielding effect is constant across a period, because electrons are always added to the same energy level. I'll get into a bit more detail in that, but let's move on to the next one. So the other one is distance, or atomic radius, which increases down the group. Down the group, the radii increases because the number of electron shells increase. Ionization energy is a removal of the valence electrons, and as the radii increases, the electron is further away, and the attraction between the nucleus and the electron is reduced. Thus, less energy is required to break it, and there is also an increase in the shielding effect. Okay, I'll get right to shielding effect now. The shielding effect, the inner electrons shield the valence electrons. Shield is like a key term that is given, that marks are given for this key term. So just check your syllabus if things have changed. The valence electrons are unable to feel the full attraction of the nucleus. For example, if the nucleus has 7 protons and there are 7 electrons, that means there's 2 in an electron shell closer to the nucleus, and there's 5 in the outside valence shell. So the closest electrons feel all the attraction of 7 protons, and the valence electrons feel the attraction of 5 protons. Sorry, that's a mistake, because 2 are shielding. Marks tend to be given just for the keyword for shielding. However, check your syllabus, and I already said that. Okay, so how does shielding effect take place when it comes to size of nuclear charge? So across the period, if you look at period 3, for example, the electrons are added to the energy level n equals to 3, and in that case, the electrons are added to the same shell. The number of inner electrons remain the same, and hence the shielding effect remains the same. Hence, as you increase the number of protons, the attraction between the nucleus and the outer electron increases. You don't really need to know all that. It's just, you need to know all of that, but you don't need to state that in your examinations. I hope this makes some intuitive sense and can help you understand chemistry a little bit better. Okay, let's analyze some trends. So from lithium to neon, there's a general increase in ionization energy, mainly because there's an increase in proton number across the period. However, there are two drops or decreases in ionization energy. First is from beryllium to boron, or group 2 to group 13. Be aware that it's group 13, not group 3 anymore, because we have transition metals. Sorry. So the valence electron in the p shell is further away than to the nucleus as compared to the s orbital. P orbital, and the s orbital shields the electrons in the p orbital. So the electron in the p orbital feels less of the attraction from the nucleus, and hence it's easier to overcome. The other one is from group 15 to group 16 between nitrogen and oxygen. As I said before, from boron to nitrogen, all the electrons that are added to the p shell are unpaired. They're in their own individual orbitals. However, in oxygen, the fourth electron is paired up, and due to spin pair repulsion, the valence electron that is paired up requires less energy to overcome, because there's repulsion between the electrons, and the electron can't feel the entire attraction of the nucleus. However, I think marks are just given for spin pair repulsion, so just take note of that. If you notice, there's a large drop in energy in the first ionization energy, which shows that the electrons are in a new shell. However, for ionization energy, it's the reverse. So if there's a large increase in first ionization energy, that means that it's in a new shell. So from lithium to helium, it's in another shell. There's one entire electron shell that's being removed. Hence, there's a large increase in energy. And by that, we've come to the end of ionization energy and electronic configuration. I apologize if there's a lot of stammering or a lot of pauses in between. This is the first time that I'm making these videos. I hope you guys enjoyed the content that I've made and you have completely understood what I've tried to tell you. Remember that this is just a brief examination guide, and it's not supposed to teach you anything. It's more like a method of revision, and I hope you guys were able to grasp some of the concepts. If you have any questions or wish to have any suggestions for future videos, please put them in the comments and we will check them out. Thank you so much, and goodbye.